Kumar, and in today's lecture we are going to study about electric field due to a uniformly charged plane sheet. Okay, so in this we can say electric field, we are going to assume a plane sheet. Let us say there is a plane sheet. There is a plane sheet of the charge density sigma. Of the charge density sigma, there is a plane sheet. Okay, and it is positively charged plane sheet. Okay, so as you can see that it is a positively charged plane sheet, and we are going to see that what is the electric field due to it. And let us assume that the charge density of this sheet is sigma. Charge density of this sheet is sigma, and the unit of charge density is coulomb per meter square. Coulomb per meter square is the unit of charge density for this infinite long plane sheet. Okay. Now we are going to use a concept, or we can say the application of Gauss law. And what does the Gauss law tells us? That Gauss law tells us that the electric flux through any area. Okay, what is the electric flux passing through any area, that we can derive by Gauss law. And in this particular concept, we are going to use the application of that. And the electric field due to uniformly charged plane sheet, we are going to derive. Okay, so let us assume that there is a Gaussian surface. There is a Gaussian surface of cylindrical shape of radius r. Let us assume that. Let us assume that there is a Gaussian surface of radius r. Okay, this is the Gaussian surface which we have made here, and we are going to see the electric field due to this infinite plane sheet at a distance r. Let us say we are going to make a point on the middle of this sheet, and this point is at a distance r. And the cylinder which we have made here, it is, we can say, divided both ways. The half of the cylinder is other side of the plane sheet, and the half of the cylinder is divided on the left side of the sheet. So this distance from here, it is also r, and we can say the length of the cylinder is 2r. Okay, and it is a non-conducting sheet. Non-conducting sheet. Okay. The word which we are using here, the infinite, we can say uniformly charged plane sheet, and it is infinite plane sheet. We can say charged infinite plane sheet. Why we are saying it infinite plane sheet? Because the distance which we are taking here, that is r distance, as compared to the plane sheet, the size of the plane sheet, it is very small. That is why we can say that the sheet is infinite. And now we are going to see that what is the electric field at a distance r, or we can say at a distance which is perpendicular to this plane sheet. Let us say if we assume that this is our plane sheet, then we are going to see that this plane sheet is placed like this, and we are going to see the electric field at this point somewhere. And this sheet is very long, or we can say in size, as compared to this distance, it is enormous. So that is why we can say that it is an infinite plane sheet, and we are going to see the electric field at this point. Or we can say on the other side also we can find out the electric field on this side. So as we know that the electric field due to a positively charged sheet, that will be pointing, we can say, normally outward. So at this point, the electric field will be pointing, due to this plane sheet, it will be pointing outward. So this will be the direction of electric field due to this plane sheet. This will be the direction of the electric field due to this plane sheet, and the area, or we can say the direction of area vector. There will be again, we can see that the area of this cylindrical surface, there will be three areas. We can say two of them are, we can say, the circular areas, left one, the left one and the right one, and the one will be curved shape. We can say curved shape area. Okay. So the area also will be pointing outwards, and the angle between area vector and the electric field is 0 degree on the right side, and similarly the area vector at this point also it will be pointing outward, and the electric field due to this plane sheet will also point we can say outward, and it will be along the area vector. The direction of the electric field will be along the area vector. So here also the angle between area vector and this n cap is the, we can say, the unit direction vector along the area vector of this particular area. Now we are going to assume that there is a let us say small area element ds here, small area element ds on the curved shape, and what will be the direction of it? It will be we can say pointing normally outward due to this surface. Let us say this is a cylinder, and now the area vector due to this side will be pointing outward, and the area vector due to this side will also be pointing outward, and the area vector due to this curved shape will be pointing normally outward in all the possible directions. Fine. So that is how we can say that for the given surface the area vector will be this way. And as we can see, that electric field due to the plane sheet will be like, if this is the plane sheet, it will be pointing normally outward, this way, outward. So it will be in the we can say this direction only. So the angle between here also the area, this will be the electric field, and the angle between the electric field and the area vector is 90 degree. So now we find out here the angles between area vector and electric field. Now our task is to find out the electric field due to this infinite plane sheet. So according to Gauss law, the flux enclosed due to this closed Gaussian surface will be closed integration over E vector dot ds vector equals to Q enclosed divided by epsilon naught. Q enclosed divided by epsilon naught. Okay. Now this closed integral, it is for this cylindrical Gaussian surface. Now it will contain three surfaces, two the circular surface and one is curved surface. So we are going to approach like that way only. So it can be divided into three parts: E vector dot ds vector for first surface plus second E vector dot ds vector plus for third surface E vector dot ds vector equals to Q enclosed by epsilon naught. Here the epsilon naught is the permittivity of free space, or we can say vacuum. Okay. Now we can Q enclosed. What is Q enclosed here? Q enclosed is the charge enclosed in this we can say the Gaussian surface. What is the charge enclosed in this Gaussian surface? So it will be due to this, we can say, particular area sector. This is the area sector which is enclosing the charge. So that is the charge Q enclosed. It is the charge density into area. Let us say if A is the area of this the circular part, then it is sigma into A. This is the charge enclosed by this Gaussian surface. So it will be sigma into A. This is the charge. Okay. Now we are going to we can say write in the vector form. It will be the magnitude of electric field and the magnitude of area vector into cos theta. So let us write that. So it will be, for first one it is E ds cos 0 degree. Let us say this is first surface, then this is second surface, and the curved one is third surface. So the first surface, the angle between area vector and the electric field vector is 0 degree. So it is 0 degree plus. For second also it is E ds cos 0 degree, and for third it is E ds cos 90 degree equals to sigma into A upon epsilon naught. Because the charge we have got, charge enclosed is sigma into A. Now this cos 90 degree, as you know that it is 0, and cos 0 degree is 1, that is why it will be. And as we can see that the sheet is infinite long, so the electric field for this particular area, it is constant. So that is why it can be taken outside of the integration. So it will be E into first ds plus E into second ds equals to sigma into A upon epsilon naught. Sigma into A upon epsilon naught. Now this ds for first and the second surfaces, as we know that the area is A. So we are going to write that, and we will get E into A plus, for the second surface also it is E into A, and equals to sigma into A by epsilon naught. Now it will become twice of electric field into area vector equals to sigma A by epsilon naught. And now this A and A will be cancelled out because it is appearing in both the sides. So it will become E equals to sigma divided by 2 epsilon naught. Sigma divided by 2 epsilon naught. So that is what the required electric field, or we can say desired electric field, due to infinite plane sheet at some random, we can say at a distance r. And as we can see that there is no dependency of the distance which we are taking from the infinite sheet. So we can say that the electric field due to infinite plane sheet is constant. It is not varying with the distance. And if we want to write out in the vector form, so it will become be E vector equals to sigma upon 2 epsilon naught nk, where n cap is the unit vector, along the area vector. Fine. E vector equals to sigma upon 2 epsilon naught n cap. That's what the electric field. I hope you got the idea, and if you like this derivation, you can like, comment, and subscribe the channel. Okay, thank you.